we will have a special point. What is the angular momentum of a rigid body about its center of mass? Okay, for the sake of simplicity, let's consider a plate and try to find its angular momentum about the centroidal axis. So you can very well see here, this is the plate, center of mass, and I have dm here, v bar is here, and you can see here omega bar is shown like this, and in the same way LC bar is also shown like this. And even you can show if there is alpha bar also like this, but I suppose all of you should know what does this mean. If I say omega bar is like this, means it's actually the vector is like this. Okay, so it's only to say that the direction of omega bar and LC are same. That's what it is the meaning of this. So here you see what is the angular momentum of this about this. It is simply, we had earlier said LZ bar is equal to IZ into omega bar.
Yes.
So here we are just changing the designation and saying LC bar is equal to IC into omega bar. Right? Right, friends?
Sir, point out, sir. Sir, the moment of inertia, sir, like IC, sir, we should take along which axis, sir, like along the axis in which angular momentum is there, or another different axis, sir?
See now, gentlemen, see. What is angular momentum?
Sir, it's the tendency of a body to maintain itself in rotational motion.
Excellent. Okay, so now the mathematical model for this was, whatever we developed here. So now we are doing this for a body, and that means first of all we have to designate the axis of rotation.
Yes, sir.
Isn't it? So when we say a body is rotating, the first thing we have to do is we have to say what is the axis of rotation. Correct?
Okay. Yes, sir.
So when I clearly said centroidal axis, that means the axis of rotation is passing through the center of mass.
Central, yes.
Got it? That is clear? Okay?
Yes, sir.
Then I have chosen arbitrary point, and the particle at that arbitrary point is dm.
Yes, sir.
And from the point on the axis of rotation, okay, that is which is passing through the center of mass, I am drawing this r bar connecting to this. Then here I have said that this body is rotating with omega bar, and therefore the velocity of this v bar has to be perpendicular to r bar. So therefore I am showing it perpendicular.
Okay, sir. Understood.
So this LC bar will be equal to IC omega bar. IC will be what? The moment of inertia about an axis passing through the center of mass or centroidal axis.
Yes, sir.
Right. And in this case, you see, axis is perpendicular to the plane of the plate. Okay, this is it. Now, what we do here is, so now we'll go over doing this. Okay, so DLC bar. What is DLC bar? Incremental momentum about the central axis of dm bar, moving with velocity v and addressed by the proximity vector or the position vector r bar. And since v bar is perpendicular,
Sir, why incremental angular momentum?
We'll start with that because we will now.
Sir, no, sir, like for all particles in a rigid body, sir, the angular momentum will be same, no, sir?
Hey, hello. How it? See, please.
About first axis.
How? Listen here, man. What is this angular momentum? dm r bar velocity bar. Is r bar same for all particles?
No, sir, no. Yes.
Okay, fine. Good. If you have doubt, you please ask or you ask me to wait. Since v bar is perpendicular to r bar, v is equal to omega, we can write it as dlc bar is equal to dm r omega. So dlc bar is equal to r square dm omega. Okay, LC bar is equal to integration of this. So we get this LC is equal to IC omega. We have already done this. Only thing is,
yes, sir.
Only thing is, with this new notation now, start getting used to it because it is going to play a very, very important role. Okay, LC bar, that means centroidal axis will simply be equal to IC into omega. Okay, moment of inertia about the centroidal axis into omega bar. Okay,
yes, sir.
That's it. It's the extension of the particle. See, I have already explained some things about it, so you know it should not be difficult for you to observe, and therefore I am just going with the flow. Angular momentum in pure centroidal rotation. Now I am designating as pure centroidal because the center of mass is at rest. It is not having translatory velocity. Understood? It's not having translatory motion. That is, only the body is rotating. Okay? It is not moving. Understood? It is only rotating. It is not moving and rotating. So therefore, I can simply write LC bar is equal to IC into omega bar. Okay. Now, angular momentum of a system of particles. Okay. Now here I am giving you a more complicated diagram here, and here you can see that the reference point is mounted on a trolley. Can you see here?
Yes, sir.
So this is only to say that you know the reference point need not be fixed. Okay. But if the reference point changes from O to O dash, then RIO will change to RIO dash. Keep this in mind. Okay. And now in this rigid body that is considered, we can see here that there are different particles chosen here, M1, M2, M3, so on and so forth, and with different velocities, V1, V2, V3, so on and so forth.
Yes.
I suppose you can see this. This is a more general case. It's a more general case. And what is important here is that you know with respect to reference. Okay. See, I want to now get the moment of inertia of this. Get to know the angular momentum of system of particles. Okay, see here, angular momentum of system of particles, right, about a given reference point is equal to the angular momentum of the system about the center of mass plus the angular momentum of the center of mass about the given reference point.
Yes.
Okay, so what you have to now see is this. See, when we said this case, what is this case? Okay, you can see here, this case is what? The body is having pure rotation.
Yes, sir.
And I made it very clear, pure rotation. I said body is purely rotating, the center of mass is at rest. That is, VC bar is equal to 0. Okay, but here you can very well see that VC bar is not equal to 0. That means it is combined motion. The body is rotating also and it is moving also.
Yes. Yes.
So therefore now, see, using the concept of center of mass, things should not be difficult at all. Okay. Only thing is, well, if I have this frame of reference here, and if I have a body here, okay, and if this body is rotating about its center of mass, omega about its center of mass. Okay, so you will get what is called as here angular momentum LC bar. If you take this C bar, will be equal to IC into omega. As simple as that. About this point.
Yes.
Okay? That is what we have. That is what we have seen. Okay. Now we will have to address it with respect to this. Now here you see, if this body is moving, so with respect to this point O, if you want to now find out what is the angular momentum of this body with respect to this point. So whenever we go to a point outside the body, then in most of the analysis, you can consider the entire body to be mass to be concentrated at the center.
Yes.
So with respect to O, this point is at rest. With respect to O, that point is at rest. So therefore, with respect to this point, the angular momentum of this point is 0. That means the angular momentum of this body with respect to this point is 0. While the angular momentum of this body with respect to this point is not 0.
Yes, yes.
Yes, sir.
Okay. And if this body also has velocity VC, then this body has angular momentum with respect to this, plus it also has angular momentum about the IC.
Yes, sir.
Yes.
Then the total angular momentum about this point will be angular momentum of this about this point plus the angular momentum of this about this point. Those are the things which we are going to understand now in step by step. Okay?
Yes.
Yes, sir. In PDF, sir, they said that the angular momentum of the system about its center of mass plus angular momentum of the center of mass. So even if the center of mass is like restricted, there will still be an angular momentum comes. So even with respect to that other point, the angular momentum body will still have angular.
Wait a minute. We'll see. We'll see under what circumstance that will come, under what circumstance it will come. Okay. Therefore, there is systematic analysis. Don't worry about it. Right? Now, amongst all these particles, we are choosing this. We are choosing this particle Mi here. Okay. So ith point is here. Mi is here. So the velocity of this ith component is V. See here. Now look at this. This is Vi with respect to O. That is, the velocity of this particle with respect to O is Vi over.
Yes, sir.
And this particle is referenced from O by this vector RIO bar. R bar of IO. This one.
Yes, sir.
Okay. Now, see, supposing we know where is the center of mass of this. The center of mass of this particle is here. Okay, we know that.
Yes.
And this point O is also known. So this point is fixed because we know where is this point and we know where is this point, center of mass. Okay.
Yes.
But now this one RIO is an arbitrary vector. Okay. So therefore now we are developing some system here by which we will be able to get this one. Okay, we'll arrive at this. What is this? See here, L bar of O, that is angular momentum of the body with reference to O, is equal to angular momentum of the body, right, with respect to its centroidal mass, with respect to center of mass, plus RC cross MVC bar. Srijan, if
Yes,
VC
sir.
bar is 0, then this quantity is 0.
Yes, sir.
See, it is like see, now earlier we have done analysis with the particle. If this particle was moving, then we were calculating the angular momentum of that. MV bar, so this is, we said here, RP with respect to O bar cross MVP with respect to O.
Yes, sir.
Right? So that V here becomes what? VC bar here.
Yes.
Right? So if this body is having no translatory motion, then only one term will be there. Otherwise, both the terms will come.
Only one term.
Only thing is, now here we are doing some rigorous analysis, because if you are given a body with these, with this type of velocity vectors, how to cope doing it? How to relate the velocity vector of the particles, etc., etc. That's what it's doing. Anyway, it's not difficult. Just write it and go keep writing it systematically. You will be able to get it, because you see, in the initial stage, if I give you L bar IO is equal to RIO bar cross MI VO. As per the definition, we are writing this. Okay, as per the definition, we are writing this. No issues.
Yes.
But what we are given here is, we are given the total mass of this body, we are given the omega bar of this body, and we are given the VC bar of this body. We are given the mass, we are given the omega bar, and we have been given the VC bar. And we have been given this point O. Now we are asked to say what is the angular momentum of such a body which is rotating, translating, having mass m with respect to O. Supposing this is what we have to arrive at. So therefore now we will start with this analysis. Okay, we will start with this analysis. So where RIO is equal to RIC plus RCO, VIO equal to VIC plus VCO. Okay, now I hope you understood this. RIO bar is equal to RIC bar plus ICO bar. This is triangle of vector addition.
Yes, sir. Yes, sir.
That should not be difficult. Now VIO bar, okay, is equal to VIC plus VCO bar. You can see here. This is concept of relative velocity.
Yes, sir.
Isn't it? This is the concept of relative velocity. Okay, because why this is done? See, now VC with respect to O. What is VC with respect to O? It is the translated velocity.
Yes, sir.
It's a translated velocity. So
Yes, yes.
you are able to get the translatory velocity component separated out, and another component is VIC. And VIC, what will be VIC? What is the speciality of this VIC? VIC will be perpendicular to RIC.
Yes, sir.
So we can separate out these two, and the vectorial combination of these two is VIO. Just imagine, when a body is there, one particle's velocity is given.
Yes.
Now you have to split it into the two important components, which is of importance for us. Because as far as the combined motion is concerned, we need to have an idea of how it is rotating and how it is moving. So VC bar and omega bar is what? And omega bar here will be what? Okay, that is it. V into I. So if I know this component, which component VIC, multiply it by Ri, then I will be able to get the omega bar of this. Right? And omega bar will be equal to VIC divided by R, will give you omega bar.
Yes.
Right? So we are able to do it. Now this is important. The total angular momentum of the system relative to the reference frame is this. See, this is important because you see, a bullet that comes out of a revolver. What did I say? Bullet that comes out of a revolver. You know what is the revolver?
Yes, sir. Yes, sir.
And what is a gun?
No, sir.
So, you see, in a gun, the bullet, when it's fired, it will go straight. Okay? In a revolver, what happens? There is a groove inside. So when the bullet comes out, it will be rotating and also translating.
Yes, sir. Okay, sir.
You remember, we use the concept of revolution. Earth
Yes,
is
yes,
revolving.
yes,
Why?
sir.
Why? It is spinning about its axis and is also translating. So a bullet that comes out of a revolver will be rotating as well as it will be translating.
Right, sir. Yes, sir.
So now its angular momentum of that bullet with respect to something. Okay, so you have to consider both the things. What is it? The angular momentum because it is revolving plus the angular momentum because it is translating.
Yes, sir. Yes, sir.
Okay, that becomes the total angular momentum at the center. I suppose you are understanding that complication, right?
Yes, sir.
See what happens. You see, gentlemen. See, the body is rotating. If this elbow of mine is the reference point, the body is rotating. Okay, you can see this elbow. The body is rotating means my hand is rotating. Can you feel that? Hello.
Yes, yes, yes.
At the same time, the body is rotating and also moving. So you will have angular momentum because of this motion, and because this vector keeps on changing because the body is moving, and my hand is also changing its angular position because it is rotating. So now you have to combine these two motions. Okay, ऐसा you have to combine this. वो combination क्या है? वो we are trying to understand. Why that is important is because you see, the angular momentum of a body is conserved provided there is no external torque acting on the body. Okay, so therefore if you want to change the angular momentum of this, then you have to apply external torque. And how much external torque if you apply, in what direction, what magnitude, then you can relate it to what is the change in the angular momentum. Okay, so that is our final goal. Okay, so therefore
Yes.
this exercise. So this splitting I think is clear here. So summation LO bar is equal to summation LI bar as usual. Summation LI bar is RIC plus RC. RC is what? I think this diagram is quite clear. Hello?
Yes, yes.
Thank you. Cross mi into so and so. So open the brackets and keep multiplying things. So you will get here 4 terms. 1, 2, 3, 4 terms. Okay. So now these 4 terms that you have got here. So you have to do a bit of manipulations here. So the first manipulation is here. Mi is put here, and here also Mi, Vic, Rc, so and so is put here. Now, following the properties of the center of mass, we can substitute here. You see summation Mi Rc. You remember yesterday this is equal to 0 because you see about the center of mass, for every particle that you see on the right, there is a corresponding particle on the left. Or if you see a particle with respect to center of mass at this proximity, then you will have corresponding particle in the opposite direction. So Mi RIC or RCC is equal to 0, okay, and Mi VIC, okay, because the moments, because the summation of all the moments of the particles about the center of mass is also 0.
Yes, sir.
So these two will get 0 dot. Okay, this term will get 0 dot, this term will get 0 dot. So we are left with only 2 more terms. So L bar of O will be equal to L RIC Mi VC and RC cross summation Mi VC. Summation Mi. Summation Mi is what? M, the mass of the body. Okay. So the mass of the body into VC, that gives you linear momentum. So linear momentum with respect to C.
Triangular momentum, so there is some R bar. Sure.
Wait. So summation M will give you the total mass. The total mass into VC. So this will give you what? The
Linear momentum.
Linear momentum. And here Mi VC RIC. RIC is this one. Anyway, it's done. Don't worry. The next step may make it very clear to you. Summation Mi is M. So put this as M. So you will get here RC cross, okay, M VC bar.
Yes.
Okay. So here you see this is RC. RC cross 1 means what? Because this entire body is translating, its angular momentum will be what? MRC. We used to write it as M V bar or RC bar cross M V bar.
Yes.
Earlier we have designated this as what? R bar P slash O.
Yes, sir.
Cross M into V C slash O.
Yes, sir.
Okay, so that is redesignated like this. Okay, so that becomes this term. And this first term, what is this first term here? Okay, RIC MIVC. What is this? This is the angular momentum of this particle. And summation of all the angular momentum of the particles about C is simply going to be what? LC.
Yes, sir. Yes.
So we get LO is equal to LC plus RC bar cross MVC. That is angular momentum of the body about its center. Imagine a bullet coming out of the revolver. Its angular momentum about its center plus with respect to my hand, the bullet is traveling towards you. So therefore, the angular momentum of the bullet because of its translatory motion, angular momentum of the bullet because it is rotating about its center of mass. So therefore, you get the total angular momentum about O is this. Correct?
Yes, sir.
Yes, sir.
Don't worry, this is not difficult. Once if you write it on your own, you will get it. Nothing to worry. But the most important thing is these abstractions that you have to get here. Okay, summation mi is equal to the total mass, and here you see you have got here the mi quantities here, and the if you take the velocity vector of this perpendicular to RIC, okay, then mi into that quantity into RIC, okay. So that will give you the moment of inertia of this summation of that will give you the moment of inertia of all these particles, sorry, the angular momentum of all these particles about the center of mass, okay. So those things should become clear to you. Okay, friends? So this final abstraction is extremely important.
Yes, sir.
Okay, see, I have made one more diagram here. Okay, what is this? You can see here, this particle is rotating and it also has VC bar. I think this is very clear.
Yes, sir.
So therefore, with respect to O, okay, what is its angular momentum with respect to O? So RC bar cross VC bar is because it is because this is moving, and you will get here because it is rotating here. Okay, then
Yes,
because it is rotating, it becomes what?
Yes,
The angular momentum is IC into omega bar.
Omega bar. Yes.
Yes.
Did you get it? And that is nothing but LC bar. Okay,
Yes.
so you can see this body is rotating and moving. I was using the term kya bolta hai, or bullet coming out of revolver and all. So you can consider this to be something like this. See, now you should get a wonderful idea, because you see, see, if you want to do something like this, that is, you want to rotate and you want to throw things. So what is the mechanism? What is the forces you have to add? Or if it is moving like this and if you want to change it, what are the things involved here, etc., etc. Okay, so this is the understanding that you should get. And another way to look at it is L bar O is equal to RC bar cross VC bar. So capital M here stands for the total mass of the body, and VC stands for the velocity of the center of mass, and IC omega bar. Okay, so the first term in the above equation presents angular momentum due to translation of the mass center, and the second term represents the angular momentum in its centroidal rotation.
Yes.
Maluma?
Yes.
Yes.
So think, if you want to ask any question, you can ask. Okay, shall I proceed?
Yes, sir.
Aram se learn, na? See, don't worry, if you are not able to learn 100% also, don't worry. Whatever you are understanding, you try to understand. These are extremely difficult concepts at your age and at this stage. At this stage, because you have to learn too many things in a very short duration, and you are continuously learning, and this age, you need time for you to relax, to enjoy, etc. But everything is curtailed. So morning to evening, you are with the books, and therefore, slightly you might feel stressed out. But anyway, if you make learning as something which gives you joy, okay, and then definitely that will enthuse you to learn better, and you will feel fresh and fine, right? See, in spite of me not feeling well, I do come and teach here. Once I teach here, I'll become so fresh. Okay. In fact, if I'm having slight temperature, I start sweating, and that means I'm relieved of the temperature, and my taste buds will be very good. I will go and have nice khana. Okay. So you should enjoy this. Please do it. That's the only way. Okay. I enjoy teaching. That gives me everything. That's my entertainment. That's my profession. That's my hobby. Okay. It gives me many things, more than what I ask for. Okay. You also should develop that sort of an attitude. And
Yes.
people who enjoy learning will never be unhappy. See, today I had to do again some hospital duty today, so I had to go. But there, what I did, I had to wait outside because somebody, the medical procedure was happening. So I took a book and I found a place. I aram se squatted, aram se I kept my book and pen and one notepad and I was aram se learning there. Okay, so in fact I prepared the model question paper for your February test series. I sat there for 1.5 hours and prepared it. And I didn't know how that 1.5 hour took place. But the other person who had come with me, he was struggling. Time what to do. He was so irritated. Okay, he was simply irritated. Yeah, how and all. I did not know how that 1.5 hour took place. That is the power of learning. All right. Now I will take you to a journey here. Angular momentum in rotation about fixed axis. Now I'll just take you slightly because now the axis of rotation, okay, or the point axis of rotation is not through the center. Here also it is not through the centroidal. Here also, right? Okay, this axis here, if you say BC, then this axis is only what? Instantaneous axis. Hello?
Yes, instantaneous.
And this body was free and therefore it had to rotate about the center of mass. Okay? Now, well, we have created a point P where the body is rotating about this point P. Please, I hope you can understand this diagram. This entire body is rotated about this point P. That is, the axis of rotation is perpendicular to this plane and passing through P. Can you appreciate?
Yes.
Yes, sir.
Yes, sir.
Now I am considering one particle, okay, and this particle, right? This particle is at C. What is C here? So suppose you say C is the C is some point here or centroidal point, center of mass. So you can see here that this center of mass itself is moving in a circle. Okay. So what about other particles of this body? Are they also moving in the circle with the same center?
Yes, sir.
Obviously.
Yes, sir.
If it is rotating about this point, every point is moving in the circles of various radius
Yes.
about this point.
Yes.
And the diagram is quite clear. So at this point, its velocity vector, at this point, its velocity vector is Vc bar. And if it is C, then Vc bar represents what? The velocity of the center of mass. Right?
Yes.
Right.
Yes.
So here we get here IP. What is IP here? So using the parallel axis theorem, you can simply shift it here. Yesterday we have learned the parallel axis theorem here.
Yes, sir.
M R of C with respect to P plus IC. Okay, so the perpendicular distance between these two is RC with respect to P square. So you can simply shift it. So
Yes,
therefore, LP bar will be equal to IP omega bar. Very simple.
Yes. Yes. Yes.
Yes, sir.
Right? So that doesn't change at all. Only you have to calculate IP and whatever is omega bar, you multiply, LP will not change. Obvious, no? Okay.
Yes.
But what you have to appreciate is the angular momentum has changed because IP has changed.
Yes.
And IP will change. IP will change if the axis of rotation is shifted.
Yes.
Understand? Now this is very important. Okay. Why should the moment of inertia change if the axis change? Why should the moment of inertia change if the axis of rotation changes?
Because it depends on position of the particular axis changes. Yes. The arrangement of the particles around axis.
Yes. So better than arrangement, you say the proximity or the distribution of the particles about the axis of rotation, if it changes, listen here, if it changes, okay, then the moment of inertia will also change.
Yes.
So now for a body, you take some body. So I have the moment of inertia at point P1. The moment of inertia is IP1. Hello.
Yes, sir.
Now I will choose another point P2 and I will say the moment of inertia at point P2 is IP2. So I have got 2 points on the same body. One is IP1, other one is IP2. Will IP1 ever be equal to IP2? Can IP1 be equal to IP2? Or it is never possible for IP1 to be equal?
Can be equal.
Yes, sir.
What about others?
Sir, I also maybe could you repeat?
See, now you take a body. I am taking some point P1 and I am saying that the moment of inertia about the axis passing through the P1 is IP1. Now I will take another point in the same body and I will pass an axis through that. I will call it as and take the moment of inertia about the new axis and I will say it is IP2. Understand? So there are 2 points IP1. Now can the moment of inertia as IP1 equal to IP2?
They can.
They can.
Yes.
Okay, Neela. Now Neela, tell me. Under what circumstance it can be?
Sir, it's a perpendicular distance from the centroidal axis will be same on either side.
Centroidal axis will be same.
Sir, if you take an ellipse about the two focus, moment of inertia will be
No, you see, Dimant, you should make it generalized, gentlemen. You cannot make it very specific like that. You cannot make it very. See, she is making a point. I'm just seeing. Okay, if its distance from the centroidal axis is same, then it is same. That's
Yes,
what
sir.
she says.
Yes, sir.
Okay. So.
Yes, sir.
Okay,
Even
okay.
parallel axis.
Okay, all of you are very good friends, supporting each other. Very good. So this is C. So this is the centroidal axis, IC. So this axis is IP1 because it is passing through P1. Okay, and you say this axis is IP2. Okay, and this is passing through P2. And since this distance and this distance are this equal, so this is x1 and this is x2, and if you say x1 is equal to x2, then you are telling that
IP1 equals IP2. Yes, sir.
So under this circumstance, if I give you a body like this, and if I say so, then IP1 will be equal to IP2. Correct? Is there any other condition attached to this?
For all bodies, you cannot apply this.
Why? Why?
So for a body which is
So we can take a compound pendulum type of object in that.
Why do you want to complicate it?
so for a
That
body,
type of object.
Don't see, compound pendulum is just an arrangement.
say for a body which is very irregular in shape. So
He makes a point.
Sir,
He makes it a point. Correct. So,
we can apply.
So we can apply now, sir.
Yes, sir. Why will we can apply?
Yes, sir.
see,
Sir,
listen,
but arrangement of mass also changes.
listen. Now,
So,
see, the body, the thing must be uniform. See, supposing this part is made up of, say, silver, Ag, and this part is made up of, say, gold.
Yes.
So there can be different point on that business like if
No, you tell me. Hey, first, why do you want to keep on asking questions? First, you answer this. See, this part is made up of different material, this part is made up of different material. Then if the moment of inertia changes, will it not change?
Sir, it should remain same.
Are you sure?
Sir, like parallel theorem is true for all bodies. Okay, we can change.
अरे यार सोचो इतनी बढ़िया है आपकी सोच देखो वो जो मटेरियल्स आप मास ले रहे हैं ना see in all that examples and definitions there is one thing what is that uniform body
Uniform.
the mass is uniformly distributed
Yes,
understand mass is uniformly distributed that's the thing see proximity will change see now if this material is heavier this material is lighter. So the proximity of this to this is so and so. But if you take the axis here, then this proximity will be more.
Yes, sir. Okay, sir.
So therefore, you see, the thing is, in this question, you should now, when you are confronted with these types of questions, okay, see, your mindset, should travel like this, it should go from one level to second level to third level to the grassroots level. Understood? And then you should come out with the answer. Okay, so because now you see, when I say so and so, I'm sure you have answered it. But again and again, I keep telling you, you have the habit of just writing it down. Yes, you are pretty sure the answer is right. But still just scribble one diagram like this and put this and so, okay. Then you think, okay, now you thought it and said this is equal. Then I said, is it under what all conditions? I gave you a hint. Then immediately you should catch upon the hint and you should try to sell. And you see, one of your friends, Pratyush, he came out. Well, if it is irregular, right? So even you see, if the body is like this, it is like this. Okay, this is the centroidal axis. But then if you shift here and here, it will not be the same. So the underlying thing is, that's why I am using the word, the proximity of the axis, the proximity of the distribution of the particles about the axis and the nature of the particles.
Yes.
Okay, that also matters. Okay, see, one of the reasons, why I am taking all these diagrams and teaching you is because you see, you should get the insight of what is happening. Andruni baat kya hai? Okay, see, I can straight away write this equation, okay, from this diagram. So from this diagram directly I can write this equation. Okay, see this equation, what I have written, I can use this diagram and write this equation. Understand? But why did I go for this? Because you may be given something where this one is not uniform. Because as far as your competitive examinations are concerned, that's where is the questions are. Because if the question is centered around this equation, okay, for uniform body, then that's it. This is the theory for board examinations and things like that. But then this is the theory for the other competitive exams. Is that clear, friends?
Yes, sir.
Yeah. So you must develop that. See, the one underlying word in all this is profundity. Profundity means the depth. Okay. So here you see the syllabus for your competitive examination is, it is wide and deep. Understand? So you understand the meaning. It is wide. Wide means the number of topics are more. See, the concepts that are discussed in your NCERT textbook are okay, fine. But now some more concepts and some more aspects about these concepts, its adaptability, its correspondence, etc. Is discussed, or some more newer ways of looking at it is also discussed. That's why I say it is wide. But you have to also understand the depth of it. Okay, so that's precisely. So if I write this diagram and I show you this, that's one depth. But if I write this diagram and explain this, this is the profundity. Okay, and tomorrow supposing I give you this body and say it is rotating with omega, half of it is made of material of density ρ1, half of it is made of density ρ2, right? And then questions are asked. Then how would you go about answering them, etc. Those are the typical things that you have to be able to. That is what is the extension of the syllabus of board into these competitive examinations. Is that clear? Hello?
Yes, sir.
Well, students, I think it's 8:30.